Dun, 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 I'll lose my mind. Put that in your bag, please. I do not. I'm not asking for an explanation. I'm just asking you to put it in your bag. All right, you guys ready? So, over the past couple weeks, we've been working on our understanding of energy, just how it gets transferred, what it looks like at different times. And so one of the things we know is that we can store energy in springs and rubber bands. We call that elastic energy, and to calculate it, we use this. All right, you developed this in your lab, 1/2 little k x squared, all right? Now, in this context, what's the little k?
Right.
The little k is the spring constant. It tells you how strong a spring is. Okay? So if you want to calculate the elastic energy, you need a spring constant. And the x is, of course, the stretch distance of the spring or the compression distance, depending on what kind of spring you're using. No big whoop. We got that. We used the internet and we looked up the formula for the kinetic energy. And that was 1/2 mv squared, where m is the mass of the object in question. M is the mass of the object in question, and v is that object's speed. Okay? No big whoop. And then, there's another one, is we could actually calculate the gravitational energy that an object has, and that one is mgh. All right. So what do you think the m is in the mgh? Go ahead, jump in. It's the mass of the object. Fantastic. And in the demonstration, we were using this little cart here. All right, you guys remember what the mass of this little cart is?
0.5 kilograms.
It is a 1/2 kilogram cart. That is correct. Okay. What is the G? What is the G?
10 newtons per kilogram.
Yeah, it's the gravitational field strength. That's exactly what it is. So our G value, because we're on the Earth, is 10 newtons per kilogram. All right, and what is the H? Height. Yeah, it's the height. It's really the difference in height between whatever two. Can you dehood, please? You two, can you dehood, please? Gracias. It's really the difference in height from where you're measuring it, like whatever the difference in height is. Is that cool? So, given this, you can just plug and chug these bad boys like no big whoop. Is that cool? All right. So, that's where we were. And so, yesterday, you were given one set of data that I created, where this was the pullback distance, and this was the distance along the track. So when we're looking at, as it goes up this track here, for any trial, the cart was going to move a certain distance. So let's say the cart moved from here to here. So this is the D, the distance along the track. And then these were given to you. I think they were 0, 0.1, 0.4, 0.9, and 1.6. Is that true?
Yeah.
Okay. Now, if you go to the second sheet, it tells you something very specific. It says that given the fact that it is a 6-degree angle, something really important is true. And at 6 degrees, it turns out that every height is a 1/10 of the distance along track because it's a triangle. That's what it says about the 6-degree angle. So it says, look, you got a 6-degree angle right here. That's the angle that this makes with the table. And then the h is a 1/10 of the d. Is that cool? So now, given that piece of information, can we fill in our height values? Well, these are still the same pullbacks. So 0, what are the values then? Well, they're a 1/10. So a 1/10 of 0, 0, so 0.01. Is that cool? I like the machinations of the brain trust out there. Well, it only says 4 hours. It doesn't say 4 consecutive hours. Is that cool? All right, so now, given that, I want to calculate the elastic energy and the gravitational energy. Now, we used the same rubber bands in spring lab 1 the other day. So what is the spring constant for the rubber bands we used the other day? Wasn't it 120 newtons per meter? Right? So I think you have enough information to calculate all of these. In fact, you have them on the lab from the other day, which is fine. And now we have enough information to calculate the MGH to get all our gravitationals. We know the M, we know the G, and here's all our H's. You guys with me on that? All right, so you're going to have to use a calculator, calculate your elastic energies, calculate your gravitational energies, and plot it, and then we'll get started with today's activity. All right? Do that right now.
What is X?
So X is the pullback distance in this case. So it's how far you stretch a spring. So it's how far back we pull this.
All right, thank you.
Yes, the pullback distance is the X in the elastic energy equation.
How far back we pull?
Nice. Do it over here. Great. Oh.
Did you prefer the?
It's 10, I think.
Okay. Well, I thought it was 10 years ago now. It's half kilograms.
Yeah, like, yeah.
I'm just going with that.
Why is the bird screaming? Alright, plot it with the end block. Listen, if you don't have a computer in front of you, use one of these, please. Alright? Come on, Lindy. What's this look? Oh, you took that there? Yes.
I just assumed, like, is there gravity for G5 because it's half, it's joules per kilogram, it's half a kilogram. So
No. So,
I thought it was 5.
no, I'm with you 100% on this. So, G is the value on the wall.
Yeah.
So, if you calculate M times G, that would be 5. But when you're just plugging in for,
Oh.
so it's 0.5 times 10
Oh.
times whatever H value you're going to use.
Is height the same every time?
What's that?
The height is not the same every time.
That's right. So the height changes, right? So
That's on-
here,
that's on
the first
five.
time it went up, it didn't go up at all. Then 1, 4, 9, 16.
Okay. Yeah.
How do I know it was here? That was very silly. that good? Yeah, that's the thing, right? Is when you stretch a spring or rubber band, the X is the stretch distance, which in this case is our pullback distance. So all the data is up there, right? So you can start on the very first slide and put in the data and do the analysis. Okay? What's that?
I can just move down. I thought it was done.
Well, you can do that data also, but you got to do the first one, and then the second one, and then the third one. Good looking parabola there, Al. Good looking parabola. I always liked the parabola, like it just made sense to me. Especially because like in your math class, they're always so decontextualized. Right? Looks like a parabola. And then you see one, you're like, oh yeah, that looks familiar. All right, another couple minutes, and then we're going to move on with our morning. Or, oh, actually,